I'm Mickey Martinson, and this is the X-Carve CNC router from my last video, in which I built a torsion box tabletop as a firm foundation for the machine, then tore down the X-Carve, cleaned it up, rebuilt it, rewired it, and got it back into operation. Or did I? At the end of that video, I equipped the machine with a Sharpie pen adapter and used it to draw some pictures. That's nice and all, but this is an X-Carve, not an X-Plot. So we have to start actually cutting some things. But before we do that, I have to set up dust collection. Call me crazy, but I am not keen on covering every surface in this garage and every surface inside my lungs with formaldehyde-laced MDF dust. Fortunately, just as this X-Carve came to me lightly used and a little neglected, so did a dust collector. Here it is. Let's get it working. I'll have to find these missing bolts at some point. What have we here? And here are those bolts I needed. Now, how to connect this to the X-Carve. This is how. We have a lot of 3D printed parts, some hardware, and a CNC machined acrylic dust shoe. The shoe is my main contribution to this. The rest of it I got off the internet. The original was made out of wood by New Brit Workshop. That was modified for 3D printing by JZ Heavy Metal, and further modified by AK Eric. Links in the description. I made this on the X-Carve itself before I knew that this was going to be a YouTube project, so I don't have any footage of that. I'm sorry. This strip brush comes by the foot from McMaster-Carr. You cut it to length and force it into a routed channel in the plate. There are blind features on both sides of this. The magnet pockets on the top, the brush channel, and the counterbores on the bottom. So making this involved routing both sides. I fixtured it with 2 pins so I could flip the part over without losing position. You can see quite a lot of chatter happened at the diagonals around the circles. That's one thing that convinced me I needed to rebuild the X-Carve in the first place. Finally, this is a 3D printed adapter I designed to connect the 2.5-inch vacuum hose. It is attached by this ring of tapped holes on the acrylic plate. Explaining how this all goes together will be much too tedious. Rather than telling you, I'll just show you. Off to the garage. First, I'll screw the hose adapter to the shoe. To install the dust shoe, I first have to remove the 2 top screws from the X-axis stepper motor. Then I have room to install this piece, the base. This strip wedges the base down, or it will once I replace the stepper motor screws. See? Firmly in place now. Next, 2 of these blocks get screwed onto the base. Here's the first one. And here's the other block. The shoe will ultimately hang from the 2 bolts sticking out of these. These 3D printed sleeves accept M5 hex nuts and make them more like thumb nuts. We'll use them for some of the adjustable features of this system. Next, we hang 2 uprights, one on each side of the spindle from the blocks we installed. The uprights have slots on them to make the height adjustable. The magnets don't really support the shoe entirely on their own, but they make assembly a little more convenient. One of the best things about this design is that the height of the dust collection is independent of the height of the spindle. You can set it where you want it and let the router make whatever Z-axis motions the job calls for. And finally, I have this super flexible hose which will connect the dust shoe's 3D printed adapter into the dust collection system with this hose clamp. Okay, time to connect this to the dust collector. And here it is. Now, setting this up to serve as central dust collection for the entire workshop will have to be the subject of another video, but I'm going to set it up in a quick and dirty way just to get this running for now. If you'd like to know why these electrical boxes have loose wires coming out of them, please see my garage lighting video to learn the horrifying truth. I will deal with this soon, I promise. We'll test this out by routing some of this MDF block. These are plastic screws, by the way, so if I get this wildly wrong and the router bit plows into the screw heads, no harm will be done. How confident are you in your G-code? I'm using a 1 3/8 inch wide surfacing bit. This one is a no-name product from Amazon, but I'll provide a link in the description anyway. The good news is that the dust collection system is working fabulously well. I can't see any dust at all here. It's all in the bag instead. The bad news is that the mill needs tramming. That is, the Z-axis is not perpendicular to the XY plane. That's why you see some significant ridges on this test piece here. To fix that, we need to know how bad the problem is. I have a dial indicator that can measure heights very precisely, but we need a flat and level reference surface to measure them from. Here we go again. The granite surface plate from my last video. Many would use a piece of plate glass for this, and that's fine too, but this is what I have, so this is what I'll use. I said this has to be flat and level. The flatness we can take for granted because this is a surface plate, but by level I don't mean relative to Earth's gravity. I really mean that this plane of the granite is parallel to the plane made by the X and Y axes of the machine. To achieve that, I have to shim the block. I have some materials of different thicknesses, playing cards, bits of paper bags from Ace Hardware, I have a lot of those, and aluminum foil. If I place some combination of these under the 4 corners of the granite, I should be able to get it level. After a lot of back and forth, I finally found a stack up under each corner that made the top surface of the block level with respect to the machine. Now we can use this to tram the spindle. To do that, we need a swing arm for the dial indicator. Here's one I 3D printed that I'm weirdly delighted by. It's a fun color and a fun shape.
about that shape. This is an offset so that I can go from the collet height and up to accommodate the dial indicator, because unlike the plate of glass that most people use for this process to establish the reference surface, I am using this much thicker granite surface plate. So I needed to design and print my own. Let's use it.
The bolt goes into the router collet, then we can swing the arm around. If the dial indicator reads constant, the spindle axis is perpendicular to the reference plane. If not, well, that's a problem. Pretty bad. From peak to valley is a height difference of maybe 50 thousandths of an inch. The spindle is pretty well balanced left to right, but is front heavy. For front to back deviation, we need to shim the Z-axis, in this case at the bottom. I went through several different types of washers in my collection before finding these, and it was a bit of a pain getting them installed. But the result is bang on. Just about 1/1000th of an inch of deviation, which is good enough for me. At this point, the X-Carve is trammed and dust collection is working well. It's time to provide it with a flat spoil board. But before I start leveling any more MDF, I should attach the machine firmly to the torsion box tabletop.
At least one member of my audience thinks the word should be pronounced torsion, not torsion. Is he right? According to the Oxford English Dictionary, yes. Thank you. I will attempt to correct my shortcomings. Now, back to the making.
Now to bolt it down. I have these right angle brackets from Amazon, which came in the smallest Ziploc bags I've ever seen. They're designed for 80/20 aluminum extrusion, like the frame of the X-Carve. You could mark the hole with pencil, but a better way to locate these accurately is to use a transfer punch. I have a set of these, and if I pick the largest one that will still go into the hole, it will mark the center pretty well. "13/64" it is. I'm going to install some self-tapping inserts designed for soft wood. These are threaded for 1024 and require me to drill a 9/32 inch hole. To make sure that hole goes in straight, I'm using this drill guide, link in the description. Experimentation on scrap showed me that the insert tends to raise a lip of wood around itself when it's screwed in. You can't get it totally flush unless you remove some of the surrounding material. So I'm drilling a shallow counterbore with one of these special bits to fix that. Now I bolt the frame down with the brackets all around the perimeter. With the X-Carve firmly secured in one place, we can finally try leveling the spoil board. As I'm not entirely confident in what's about to happen, I'm going to try leveling another piece of MDF first. You can see I've tried it already with this one before the rebuild project began. The ridges we saw before tramming are gone, but there's something else wrong. Look at this wavy periodic thing happening over here. What could be going on? Here's one possibility. The spoilboard isn't very stiff. The indicator here is pretty close to the middle of the span. Look at how much vertical deflection I can produce with just the pressure from one hand. I've removed the spoilboard entirely and investigated the play in the z-axis. This center member here isn't adding much to the structure now that the rest of the frame is bolted down. I could bolt this down as well, but now that I have it open, I'm wondering, what do I need this for at all? I could just remove this, gain back a little bit of extra breathing room in the z-axis, and attach my spoilboard directly to the torsion box. Here is a sweet piece of laboratory scrap I found once. It is a 1/2 inch thick aluminum plate, 2 feet square, with a grid of tapped holes. I think it was a fixturing plate for optics experiments. The holes are 1/4 and the grid is 1 inch on center, by the way. This should add at least some local stiffness to the bed of the machine, and the holes might add some convenient mounting options. Although it's pretty flat overall, there are a lot of scratches and dings that add height variations. But that's what the spoilboard is for. I have to lean on this with both hands to get as much as 4/1000ths of deflection. That's as good as this setup is going to get. I've made an MDF spoilboard specifically for this aluminum plate. Let's install it and try leveling that. Hopefully the increased bed rigidity will give us a better result. Nope, after leveling the entire new wasteboard, once again there is a periodic artifact on this surface. We could call it scalloping? At this point I removed the stiffening screws, thinking they were introducing some kind of distortion. You may have already figured out what happened here, and you may be shouting at your TV by now. I don't blame you. You will be satisfied, I promise. Hang in there. Still the same periodic scalloped surface. At this point, I finally asked the question, what exactly is that period? How long is it? Looks like it's a little less than 2.5 inches. And what is the diameter of the V wheels? Roughly 0.75 inches. The circumference of 0.75 inch diameter is, well, would you look at that? Just under 2.5 inches. Most likely, that periodic scalloping effect is being caused by at least one of the wheels being out of round or otherwise janky. Every time it makes a full revolution, the same deviation happens. So I'm going to have to take apart the x-axis and find out which wheel is causing the trouble. Since I'm going to tear the machine down yet again, I'm going to take the opportunity to add some extra stiffening. The y-axis rails are unsupported except at their ends, so they are not very stiff, as I shall now demonstrate. So we can add some supports. Here is a piece of aluminum 2 inches wide by 1/8 inch thick. We can insert it into the gap between the frame and the rail and bolt it to both, which will make the y-axis much stiffer. The only problem is that the gap isn't quite 1/8 of an inch. I could loosen the screws and move the frame members inbound somewhat, but the holes in the brackets won't line up with the holes in the tabletop if I do. I could drill more holes in the tabletop, but I don't want to make Swiss cheese out of it. What I need is a bracket with a slot, so that I can shift it a little and still use the original insert holes. I could just modify the originals with a file or a Dremel or something, and I probably should. But I could make a cleaner hole if only I had a milling machine. Right, we can use the X-Carve to improve the X-Carve. Here is a fixture I 3D printed. Off camera I installed another heat-set threaded insert. The brackets will be held on by one screw, and the fixture will bolt onto the aluminum plate. This is an 1/8 inch diameter single flute upcut carbide router bit, said to be good for aluminum. Let's try it. I guess I should have tightened that screw properly. Let's try it again. In addition to tightening the work holding better, I've slowed down the program to reduce the stresses on the bit and on the machine. With that dialed in, I'll add slots to the rest of the side brackets. The surface finish is really good. It's not exactly centered, you can see it just kissed the paint on one side of the original hole, but overall, I'm really pleased. Now let's make some of those Y-axis supports. I'm using a stop block on this miter saw so I can produce 6 supports, all 100 millimeters long. I need to make a hole pattern that looks like this. So the frame member at the bottom gets 2 screws and the Y-axis rail at the top gets 4 screws, 2 in each slot. Could I lay this out by hand and make the holes on the drill press? Of course. At only 6 units, it may even be faster and easier. But never mind that. I now have a CNC hammer. And all the world is my CNC nail. The fixturing plate might not be the most useful thing when the entire surface is covered up, but it definitely comes in handy for setups like this one. I'm using MDF scrap as a mini spoilboard, socket head cap screws to locate the blanks, and the hold downs that came with the X-Carve to secure them. Based on my experience with the angle brackets, I've decided to add a 3rd clamp for extra security. I won't claim this is the most efficient program for making these parts. I'm learning as I go, and there's obviously much room for improvement, but that's another show. After a quick and dirty paint job, these are ready for installation. But first, it's time to deal with the real problem. That is, the wheel problem. Right, I've taken it apart once again. The process is a little tedious by now, so I didn't show it on camera. But we covered it thoroughly in part 1 of this series, which if you haven't seen, go back and watch it now. Most importantly, I have brought the gantry of the X-Carve into the air conditioning. No. The garage still isn't air conditioned, but we're getting close. Like, comment, and subscribe. The potential problem wheels are all here in the carriage. Some of them are smoother than others, but there's nothing obviously wrong with any of them. The right way to proceed is probably to build a testing jig and use the dial indicator to measure the runout of each one. But that's a lot of work, and here is a batch of new V-wheels I bought from a no-name company on Amazon. I was worried that these new wheels are not exactly the same as the originals. The tire, if you will, is thicker and encloses more of the bearing, but the height of the center of the V appears to be identical. For what it's worth, the new one at least feels a little smoother. Let's just replace them all and see how well that works. Yikes. I'm sure that'll be fine. Keep going. Well, it definitely feels smooth enough. Is it good? I don't know. Only one way to find out. Let's continue with the assembly. At this point, I'm adding those reinforcement screws back to the X-axis. See my last video for more about this modification. This time, however, I'm adding extra screws because why not? I did it again. I've made this mistake before. You cannot put the belt on when the carriage is already on the gantry. So I've got to take it apart again. Let's do it. Now that's done, let's bring the gantry back to the garage and try out all of our new modifications. Okay, people. This time I'll get the belts done first.
y-axis stiffeners are now determining the gap between the rail and the frame, so we can tighten down the slotted brackets. Now for a somewhat unscientific demonstration of the benefit of this modification. Before adding the plates, we have about 30,000ths of an inch of deflection when I lean on the spindle with my precisely calibrated hand. And with the plates, about 1/3 of that, with most of the resulting 10,000ths probably due to twisting of the gantry more than to bending of the y-axis rails. With that done, I trammed it again. Next, I brought back the Spoilboard. Finally, I reinstalled dust collection. Time to try leveling the Spoilboard yet again. So what's wrong now? There are significant ridges running along the x-axis, but these aren't due to the spindle needing tramming. If that was the reason, the ridges would all be high on the same side, created on each pass, instead of being high on both sides in a periodic pattern. Now, for some reason, I didn't take the opportunity to replace all the wheels when I last had this taken apart. I only did the x-axis, not the y-axis. The period of this ridge pattern doesn't correspond to a full rotation of the wheels, but we're not sweeping the bit along the y-axis, we're moving it in steps and sweeping along x, which maybe could account for that? I'm not sure, but let's try it anyway. That means tearing down the machine yet again. Adding those extra supports makes this a lot more convenient. Now, when you take off the end plates, the y-axis rail doesn't collapse, so it's easier to slide the gantry on and off. That doesn't save you from being an idiot, though. Yikes. Fortunately, it fell on a cardboard box that took some of the impact. I don't think there's any damage, so let's keep going. After reassembly and tramming once more, we're ready for another servicing test. Well, that's no improvement at all. It might even be worse. Let's try surfacing along the y-axis instead. Same phenomenon. It seems like the height of the cut is different depending on which direction the router is traveling. But how bad is the problem? Only by measuring can we really know if our tweaks are helping or hurting. According to the dial indicator, the high stripes are about 0.008 above the low ones. It does stay consistent across the entire surface, at least that's good news. But why does the direction matter? To speed up testing, I made these MDF blocks that I can flatten with a few quick passes. First test, I'm going to try cutting only in one direction rather than boustrophedontically. Boustrophedontically? It's a Greek word. It means turning like an ox. You plow the field in one direction, turn the ox around, plow your way back. Some languages are written this way as well, right to left, then left to right on the next line. That's what we've been doing with the router. But instead, we can make a change in our software, in this case Fusion 360, such that we only route in one direction. You can see that the setting was both ways, and I'm changing it to climb milling. More on what that means later. Well, that's not bad at all.
There are some tool marks that you can see under raking light, but it passes the all-important fingernail test. I mentioned climb milling before. The other direction you can choose is conventional milling. In both cases, the bit is the same, rotating clockwise. The only difference is the direction of travel. Now, you can remember which is which by thinking that in the case of climb milling, the bit is climbing its way up the cliff made by the cut surface. Whereas for conventional milling, the bit is pulling itself down into the workpiece. The forces on the router are very different in these two cases, which is why direction of travel is so important when you're routing by hand. It matters for CNC too. If the machine was perfectly rigid, maybe it wouldn't, but with this X-Carve, as we saw, the difference between the loading scenarios was enough to change the height of the surface by 0.008 of an inch. For some reason, I wasn't thinking clearly about this. My mental model was all screwed up. I imagined that the bit was climb milling on one side and conventional milling on the other, so the forces would be the same no matter which direction you went. And that would be true if you were just plowing into the middle of the workpiece. But you're not. You're making successive overlapping passes. One side of the cut is already gone, so direction really does matter. Well, now that I've got that all figured out, there's nothing left but to try it on the Spoilboard itself. At this point, the phone I was using to film this shut down, probably for thermal reasons. Remember, we still don't have that AC. I'm sure you've liked and subscribed already, but don't be shy. You can comment more than once. Anyway, this Spoilboard is looking pretty good. We can work with this. As with the test sample, you can see tool marks along the y-axis, but you can't feel anything. And you might be surprised to find just how small a lip you can detect with a calibrated Mark I fingernail. For now, this is more than good enough. After all, I've got parts and other videos to make. See you soon.